Hello, fans of parametric methods. We will do a quick example here of, of a model that I would like you to just take a peek at here. So we have a pin at the left end and a roller at the right end. And we have a simple frame with a moment carrying connection here. The nice thing about this, I think, is that we can move the position of the load anywhere we want. We could change the magnitude of the load. And obviously we could do self-weight and things like that, but I wanted to keep it with a point load for this exercise. And then another really nice thing is we could change the span of our structure and we could change the height of our structure. So it's all pretty quick to draw. I could show you how to do this. It's all within Grasshopper. There's no actual Rhino geometries here. It's 100% Grasshopper. But it's just essentially connecting points with a line. And I called it the right column, the beam, and the left column. And then displaying the loads, that's not so hard. But then we move into Karamba here. So one thing to point out is that we can put in a Young's modulus if we want, anything we want. So for like a homework problem, we put in typically 1 million pounds per square inch, which is 1,000 kips per square inch. Make sure you get the shear modulus using the expression here. Just so you don't have to do this by hand, E over 2 times 1 plus nu. That's not hard. And that material goes into the material component for the assemble. The elements are the 3 sticks that I drew, but you can't just pull in lines. You have to use the line to beam component here. So now it becomes, from a geometric entity, it becomes a finite element. The supports here are very, very flexible. So we want the left support, and notice I labeled these so that you can kind of say bottom left, bottom right. And then that's the triangle. But the supports here, translation is locked. And then rotation about the x-axis so that we don't have the instability out of plane, but otherwise free to rotate. And then the other one just has a y translation restraint and a z translation restraint, but nothing in the x direction. It's allowed to slide. And then again, that flopping over about the x-axis. So I just put those in as the support conditions. The load is just grabbing that vertical downward load, the unit Z. I almost said Z, but then it's negative here. So it's going down. And that's about it. Oh, the cross section, I put in my own cross section in here just as a trapezoid. These are inches, so be careful with that. If you're confused about the units, which I am in imperial units here, hover over it, and Clements says inches, and it is inches. Whereas the load, it says kips, and the modulus is kips per square inch. So be careful with all that. It's consistent, it works. Just be careful with it. Okay, so we got the loads, and then we can analyze the model. And I can get the maximum displacement here, which is inches. And then I could get the display. So now this is where it gets really nice, I think, because the students can see that as I move the load around, you know, different things happen, right? There's no bending at all. And there's a lot of bending in the beam here, but there's no bending in this column. Can you notice that? If there's no bending there because there's no horizontal load, that's the roller, then there's no horizontal here, and the bending moment is 0 on the other column. But this is super sweet because I could also obviously change the magnitude of the span or the magnitude of the height, or of course the magnitude of the load. And then for no extra charge, we get the bending moment diagram. So the bending moment diagram is shown here in a front view, but we could certainly look at it in perspective view also if we wanted to. And we see the bending moment diagram. And that makes perfect sense as we mentioned before, there's no bending there. But then watch this. This is super cool too. So I'm going to leave the so the faint line here is the bent beam that's in there. And then the more clear line here is the bending moment diagram. But watch what happens if we restrain, for instance, this roller. Now it becomes a pin. Now suddenly you could see the bending moment diagram goes to 0 at the pin. And now it's growing and it matches the bending moment of the beam. That's nice instantaneous visual feedback. And we could see how that plays out. And then finally, the last thing you want to do is perhaps play with the rotations. And now you just restrain the right side and the left side. And now there's bending moment at the base. You can see it here, right? You could see the bending moment at the base is non-zero because I restrained it in. There it is, okay? So you could just restrain it the way you want. You could play with the virtual work method, haha, if you want to get the displacements, but obviously the displacements will be smaller than they were in the more flexible case with the other fixities. So that's pretty cool. And then in the next video or some point, we'll recreate this in Python using GH Python. And then we could do the hand calculations right in here in this environment, that's what we want to do. Okay, hope you enjoyed this. Bye. Like, subscribe.